Let's be honest, when you look at the periodic table, it can seem like just a big grid of boxes, right? Well, today we're going to change that. We're going to take a journey, a deep dive, to uncover the hidden story, the incredible narrative that's packed into just a single row. Period 3. Okay, let's get into it.
And right at the heart of this story, there's a real puzzle. How can sodium, a metal that's so reactive it literally explodes in water, and argon, a gas so unreactive it's called inert, how can they possibly belong in the same row? It seems totally impossible. But trust me, by the end of this, you'll see exactly how they connect.
So how do we solve this? Well, every good journey needs a map. And for us, that map is the modern periodic law. It's a simple but powerful idea. Everything is organized by atomic number, and because of that, properties change in predictable, repeating patterns. You see, it's not just chaos, it's a code. As we add one proton and one electron at a time moving across the period, the forces at play shift in this smooth, logical way. And today, we're going to crack that code for period 3.
All right, so let's meet our cast of characters for today's journey. These are the 8 elements that make up that third row of the periodic table, and we're going to travel from left to right.
All right, here they are. We've got sodium, magnesium, and aluminum. Then comes silicon, phosphorus, sulfur, chlorine, and we finish with argon. You know, even just listing them out like that, you can almost feel the shift, can't you? We start with these classic solid metals and end up with gases. That very obvious change from metal to non-metal, that's really the heart of our story. So, our journey is going to start in what I like to call the metallic kingdom. This is where we find our first 3 elements: sodium, magnesium, and aluminum. This is pretty familiar territory, defined by all that classic metallic behavior.
So what is it that makes a metal, well, a metal? It really comes down to this idea of a sea of delocalized electrons. Just picture it. The metal atoms are like these little islands floating in an ocean made of their own outer electrons. These electrons aren't stuck to any one atom. They're totally free to just flow through the whole structure. And that free flow of electrons, that is literally what an electric current is. It's why they conduct electricity so incredibly well.
But here's the thing. Even within this kingdom, not all of the metals have the same personality. I mean, look at sodium. You drop it in water, and it's a violent, explosive, super energetic reaction. But then you look at its next-door neighbor, magnesium, and it's way more chilled out. It reacts pretty slowly with cold water, only really getting going with steam. This shows us our very first trend. Reactivity actually decreases as we move from left to right. All right, so after we leave the metals behind, we hit something totally different, a great divide. This is the turning point in our journey, and its name is silicon. This one element is basically the bridge between 2 completely different worlds. And wow, this chart just says it all, doesn't it? Look at this. The melting points for the metals on the left are pretty high, which makes sense. Then we get to silicon and bam! The melting point just skyrockets to this massive peak. But then, right after, for phosphorus and everything else, it absolutely plummets. So what on earth is going on here? The secret? It's all in the structure. See, unlike the metals with their free-flowing sea of electrons, silicon forms what's called a giant covalent lattice. The best way to think about it is like a diamond. Every single atom is locked into place with its neighbors by these incredibly strong, rigid bonds. So to melt silicon, you have to start breaking those powerful bonds all throughout the structure, and that takes a huge amount of energy.
Okay, so once we get over that massive silicon peak, we walk into a new and final territory. The molecular world of the nonmetals. And in this world, the rules of the game are totally different, which explains that crazy drop in melting points we just saw.
So listen, this is the most important point right here. On the left side, the metals and silicon, they're what we call giant structures. The whole chunk of stuff is just one big network held together by strong bonds. But on the right side, we've got these little individual simple molecules. Now, the bonds inside a single phosphorus molecule are super strong, but, and this is the key, the forces holding one molecule next to another molecule are incredibly weak.
And that, right there, is the secret. To melt phosphorus or to boil chlorine, you don't have to break the strong bonds inside the molecules. You just have to nudge apart the weak forces between them. And that takes almost no energy at all, which is exactly why they're either gases or really soft solids with super low melting points.
Okay, we've seen the elements themselves, but the story gets even richer, even clearer when you look at the compounds they make. So let's check out their oxides and their chlorides, because they show us another pattern across period 3 that's just as beautiful and predictable. So let's head back to the far left again, back to our metallic kingdom.
When you burn sodium and magnesium in oxygen, you get their oxides. And if you take those oxides and pop them in water, they form strongly alkaline or basic solutions. This is classic, textbook metallic oxide behavior.
Okay, next up we get to aluminum. Now, its oxide is kind of the great diplomat of the period. It's what we call amphoteric, which is just a fancy way of saying it can react with and neutralize both strong acids and strong bases. It sits perfectly in the middle of the acid-base spectrum.
And you can probably guess what happens next. Once we cross that middle ground with aluminum, the trend becomes crystal clear. The oxides of silicon, phosphorus, and sulfur, they're all acidic. When they react with water, they form some pretty famous acids, like phosphoric acid and the incredibly powerful sulfuric acid. So there it is, a perfect, smooth transition, basic to amphoteric to acidic.
And this pattern is just as dramatic when we look at their chlorides. We all know what happens when you put sodium chloride, table salt, in water. It just dissolves, peacefully, no drama. But now look at silicon tetrachloride. It doesn't just dissolve, it reacts violently, spitting out these steamy acidic fumes of hydrogen chloride gas. It's a completely different response.
So why? Why does one just kind of disappear into the water, while the other one puts up this huge, violent fight? Well, the answer, once again, comes right back down to the fundamental nature of these elements. It's all about the bonding. It always comes back to the bonding. The chlorides on the left, like table salt, are ionic. Water molecules just gently surround the positive and negative ions, and poof, it dissolves. But the chlorides on the right, they're covalent. They're these small molecules that water can physically attack and literally tear apart. That reaction is called hydrolysis, which means split by water, and it's that chemical breakdown that releases all that acidic HCl gas. So let's just zoom out for a second and look at our completed map. I mean, just think about what we've seen. Across one single row of the periodic table, we've traveled from highly conductive metals all the way to complete insulators. We went from elements that form basic compounds to ones that form powerful acids, from chlorides that just dissolve peacefully to ones that react violently. None of it is random. It's a complete, predictable, and frankly beautiful story of chemical change, all driven by that simple, steady, step-by-step increase of just one proton at a time.
The journey across a period tells this incredible story. But you know what? That leaves us with one final, really tantalizing question. If this much change happens when you just move from left to right, what new story, what new patterns are waiting for us when we decide to travel down a group? But that's a story for another time.